Hello, everyone. Welcome to this episode of Conscious Design. I'm Ian Peterman, your host and author of the book Conscious Design. And with me today, I have Chris Stern, CEO and co-founder of CarbiCrete. Welcome to the show.
Thank you very much, Ian. It's great to be here.
Yeah, so you guys are doing some really great work in replacing concrete or improving it. So that's a huge task. that's a huge undertaking. So I'd love you to start with, what is your journey like? How did you arrive on this particular problem as something you wanted to solve?
Well, interestingly enough, I was coming off the heels of my last startup. I was in solar power before, and I was a co-founder at a company called Pure Energies, which was a residential solar provider, which we sold in 2014 to NRG Energy, an electric transmitter in the United States. And after several months of not doing anything, I was looking for something to do, actually. And I was introduced to the folks at McGill University, where I learned about cement. And I learned the difference between cement and concrete because they're different. Cement is the glue and concrete is the form factor. It's the stuff you see that's being poured or put into bricks and things like that. And I learned that cement is actually extremely carbon intensive, which I had not known. Like if cement were a country, it would be number 3 in terms of carbon emissions. So cement's responsible for about 8% of CO2 emissions every year. And it's impossible to stop that because you can use different fuels to convert the limestone into clinker. But the issue is that as you're doing that, as you're cracking the calcium carbonate, CaCO3, you're tearing off CO2. And the only way to stop that from happening is to either capture the CO2 or use a different material. So the folks that I met at McGill had discovered that you can use an industrial waste byproduct called steel slag, which is about 12 to 15% by weight of steel production. So if you have a ton of steel being made, 120 to 150 kilograms of slag is produced, and it has to be produced. That it's part of the process, and it actually makes good steel. But it is something that is basically just a byproduct. And a lot of times this byproduct is it's actually landfilled. It's not dangerous. It's just very calcium-rich minerals, and so
it's just like an inert but kind of useless material to the steel
yeah.
industry.
A lot of times, other than landfilling, what they use it for is as aggregate underneath roads. So it's an inexpensive gravel, as it were. But now we've repurposed it to replace cement as the binder in concrete. It's very rich in calcium silicates and calcium oxides, which lend themselves very well to reacting with CO2. So we do 3 things. We eliminate the need for cement, which is highly carbon intensive. We find a new use for an industrial waste byproduct, which is typically landfilled, called steel slag. And by the way, the only way to cure this steel slag-based concrete is to react it with CO2. So the CO2 is uptaken by the slag, and it's forever part of the concrete, to never leak out.
So you're making it so you don't create any off-gassing, and then you're actually absorbing it.
Exactly.
You're actually pulling it back out of, and does it just do it not like when you cure it, it just pulls it straight from the air? Or
no, it's not. It's not that. I mean, over the course of time, yes, it's a natural product. Like it's natural. That's how calcium carbonate's eventually made. But in our case, we greatly accelerate it by putting it inside a curing chamber where we subject it to CO2, and the CO2 reacts with the calcium oxides and calcium silicates. So it's not an atmosphere; it's actually in an enclosed chamber.
Got it. And are you able to how are you getting that CO2? Is it other industrial waste that you're collecting?
So currently we get it from one of the gas producers, and in fact, in our first plant here, it's being collected at a ethanol fermentation plant. So it's a biogenic source. So we're not burning fossil fuels to make the CO2. It's as a result of ethanol fermentation. And then it gets inserted into the curing system where it reacts with the steel slag.
So you're taking two industrial wastes and putting them together into this material. I mean, if we were to break it down really.
Yeah, and making a very useful building product that you can explain to your grandmother. Everybody understands what a brick and a paving stone is, and concrete blocks. So that's why it's a unique solution to climate change. It's one of the solutions that's easily explainable to a lot of people, because a lot of these solutions are difficult to explain. Like you're taking CO2 out of the air and you're sticking it into the ground, and like people have a hard time with that. This is we're taking CO2, the other industrial waste, put it all together in a box, and out comes concrete blocks that you can use to build a home.
And so your process, so you mentioned making the bricks, right? Cinder blocks, essentially. Is that the primary? Is that for the material, is that the best use? Can it be poured? Is it kind of what can you do with your material?
Well, there's several different types of concrete. What we're talking about is masonry, which is dry cast. So when it's formed inside of a concrete machine, I mean, it's not dry, but it's not liquid. You can't pour it. It's like wet sand, and that's called dry cast materials. And so, like, what is a dry cast material? A concrete masonry unit, so a cinder block. It's a paving stone. It's a retaining wall. The things that you would buy at Lowe's or Home Depot, for your backyard or for your driveway, Then you've got precast materials. And precast materials are like jersey barriers that you see on the roads. They're like, precast balconies that you would see on a condo. Those are precast materials. And then the final thing is ready mix, which is the trucks that you see rolling around that pour into formwork. And those are the three basic types of concrete. So right now we're working on the dry cast portion, which is masonry. And we're also doing research and development on wet cast. For wet applications like jersey barriers and other things like this.
Got it. And so is there any difference material wise? Is it able to, are your cinder blocks able to handle similarly? Is it, material strength and things like that? Similar? Is it better? Kind of what would be the comparison if someone was looking between, the sustainability side, right?
It's similar or better. I mean, we really design the strength according to the application. So we can turn up the strength or turn down the strength depending on what we need to do. And the interesting thing is that the stronger the material or the concrete, the more CO2 is actually captured. So it's really? It's like a positive feedback, right? So if you make a really strong piece of concrete at 75 MPa, it's really soaked up a lot of CO2.
Oh, interesting.
Yeah.
That's a really good benefit then. Stronger.
It's one of those too good to be true situations, right? Like we're doing three things, right? Getting rid of industrial waste, CO2, making concrete, and capturing CO2.
And making it stronger makes it absorb even more CO2, which usually that's where you would see the opposite. You're like, well, where's the drawback at some point?
There aren't any drawbacks, to this product. Actually, I mean, the fact remains is we're scaling up, and people are going to start using this material. Anywhere within 150 miles of a steel plant, our product is going to be the product of choice.
Got it. And so long term, you say you're scaling. So are you scaling based on, basically just going where a steel factory is? Because I mean, obviously it keeps your transportation low. You're not shipping heavy waste across the country to make something. Is that what you're looking at, or how are you looking at scaling this?
Yeah. So there's a couple of things there. The first thing to look at is, first of all, we license our technology to existing concrete producers. So we're not out there, we're not building CarbiCrete plants, we're licensing the technology. And the concept is to create clusters of companies or clusters of licensees that are not too far from steel plants, to obviously minimize the amount of fossil fuels burned to bring the things all around, but also the cost that's associated with it. So all those things coming together when we decide where to go next.
Got it. And as you're licensing it out, what is the general response? Or is it is it too cost prohibitive, or people really willing to go? Kind of what's the reception been so far?
Well, the cost, actually, the materials cost is lower, because we're using
Even
it.
better.
When you factor in, obviously there's some CapEx involved, it's about the same price. So people are actually contacting us. So it's not something that we're out. We haven't done a lot of outward marketing directly towards companies. People have been coming to us based on what they've read in the news or heard on podcasts.
Right. Right, like this.
Yeah.
Well, so there really are no drawbacks if it's cheaper and better, or similar and better in every single way. It's really a no-brainer at this point.
It is a no-brainer. Yeah, 100%.
Why wouldn't you use this? And because you're the same strength, you're able to, any application that somebody would have, a regular cinder block or anything, you're able to meet that. And is there how is scaling like volume? Is the production pretty similar? Is there specific challenges around producing ton of these, or is it pretty much the same process? Are you able to use like the same equipment to mold it, for example?
Yeah, for the molding equipment, it's exactly the same. The batching equipment, the only thing that changes is the curing system. The curing system's got to contain CO2. The standard systems today use heat and steam, and they're not hermetic. So we need a hermetic system because you're putting CO2 in there. So that's the biggest difference. So scaling is not that difficult. It's just that you need to have different curing systems installed in the plant.
Right, but you're talking about only one piece of equipment rather than a whole. You don't need to, if you wanted to, convert your entire production facility to this material, you would be replacing, one type of equipment rather than a whole system-wide kind of gut and replace.
Hence the licensing model. All the equipment's already out there already. So why not just leverage all that? We don't need to build our own masonry plants because they all exist out there.
Right.
And the sales channels, all that. It's a business that's been going on for hundreds of years, right? So we don't do upend that. We just need to upend how things are done.
Got it. And as you're going through this, so you mentioned a little bit kind of your long-term research that you're doing. You're looking to get into the next zone. Is there, as you've been doing this, is there any similar products? Is it kind of what's your long-term goal here with this material? What you plan to do with the company?
Yeah, so I mean, my long-term goal is to utilize every extra piece of steel slag that we can find and turn it into concrete. So that if we do that based on today's numbers, we can make 1 billion tons of carbon negative concrete. And with process improvements and reclamation of old slag, we could get that to 2 billion tons of carbon negative concrete per year. So that's the end game for us. That's our North Star and where we're headed.
And how does that line up with the global production of regular concrete? Is that enough to totally replace it, or?
No, it's not. I mean, the global usage of concrete right now is the second most used material in the world, after water. And so there's about 30 billion tons of it made every year. So that's why I said we're part of the solution to climate change. And 1 billion tons of concrete is a lot of concrete. So
yes, it is.
Regardless. Yeah.
Got it. And so is this steel slag that you're talking about, is that the only only source of it then is the processing. So you have your I guess your cap, so to speak, is the output of the slag. Is that?
Yeah, I mean, there's that, and obviously process improvements. We've already invented a new way that'll see us have I would say, a 40% decline in the amount of slag that we need. But like,
Okay.
there's so all those things will allow us to, be a bit more conservative with the slag usage, and therefore be able to make more concrete. So that's an ongoing R&D.
Right. Well, that's good. So there's obviously ways for you to be able to optimize that use,
Yeah.
that slag usage, and still make a concrete that's that's usable. Is there? I mean, you talked about there's many different kinds of use for concrete. Is this something that would ever be able to apply to like roads? Because there's still concrete roads, concrete sidewalks. Is that an end goal, or are you sticking with more of the molded?
There are some opportunities for us to get into other markets like that, but I think what we'll see our company do is cover the masonry market, and then get into the precast market, like Jersey barriers and things like that, pipes. There's a lot of concrete pipes made. So I think probably in the precast world, after masonry, I think pipes will be our next invention or scale up.
Got it. Well, that's still, there's a lot of pipes. I've done some projects on the pipe end of things, and there's a lot of concrete pipes that we put in the ground. So
Yep.
that's a huge piece, and so that's great. That's still a huge amount of, if you can produce 1 billion tons, that's a lot of concrete.
Well, look, we're trying to take 150 million tons of CO2 off the table. And that's it's something that we can do, and it's not 40 or 50 gigatons, but it's on the path to getting there. And like I said, there's many different solutions to climate change, and ours is a no-brainer. It's not like direct air capture and sticking it into the ground, which costs $1,200 per ton, right? This is not a cost center. This is something that makes money for somebody.
Right. Well, and not only does it make money for someone, it is replacing at an equal cost a material that is a problem and replaces the one that undoes some of the problem by itself, which I have no idea why anybody would be able to say this isn't an easy no-brainer to just pick this material.
Yeah, this is like, not to use a cliche, but it's low-hanging fruit, right? Yeah.
Right. Well, that's great. I mean, it's great to see that there are low-hanging fruit, because I think that's one of the things people are so, they want change. I recently heard a report that 80% of Americans all agree climate change is a problem, which I think is the only thing we agree on that majority of as a country. So that was impressive alone, and there happened to be over climate change. But there's, even when I talk to people, there's still this idea of everything is still more expensive. And there's not solutions that are equal cost that are actually better. So and such low-hanging fruit, this is an easy swap. It's great to hear that there's more. There are those low-hanging fruits.
People like to say that this will cost more, it's going to cost that in the end, but what is the cost of not doing it? And secondly, to create all the things that we have these days, like the interstate system in the US, the electric grid, all these things required some input from the people, right? And once it's done, it's done. When the infrastructure is done, it's done. So
right.
I think people need to look at it like that. And that it's an investment, yes, but in the end, you get something that can last a long time and changes the way people do things.
Yeah, I love the highway analogy, because I don't know anybody that remembers or thinks about the fact that we didn't used to have an interstate system, right? That was a huge undertaking to interstate all of the US. And it's just like, we're all so used to it because we live in it. We just hop on a highway, and I can go to any part of the country. I can leave to Canada and Mexico on interstates that have been built way before I was born. And it's just, they exist, right? They just do, and we kind of take it for granted, and we don't remember that it took a lot of time and money and effort to make that happen. But now it's, it's great. Right?
Well, the same thing with
benefiting for years.
the same thing with railroads, electric grid, water infrastructure, all that. We take it for granted, but it was paid for, and now people just use it as at will. Same thing with internet, right? Internet's something that's happening in our lifetimes, and take that for granted. But there was a huge cost to get fiber optics everywhere.
Those cables in the ocean didn't just appear.
Yeah, exactly. So you can call it more expensive, but I mean, it's like solar panels. Once you've paid for them, you just set them up, right? And the electricity flows. You don't have to feed natural gas into it. You don't have to feed, oil or coal. It just kind of happens, right? Due to the photovoltaic effect.
Right.
Photovoltaic effect, sorry.
Yeah. Yeah, exactly. Well, this is super exciting for me. There's so many. I've talked to people that have more complex solutions for concrete, but they're long term. They're not. They require a new factory, or they require a lot of investment. So it's great to see that there's these options where no, we can just swap out a material, keep your plant, replace one machine, and you are now. And if you do it right, I feel like you're a carbon negative or close by the time you're.
We are carbon negative, yeah. We make a carbon negative product. It's been reviewed by 2 different agencies. Our life cycle analysis is carbon negative, so we consume more CO2 than we emit.
That's amazing. Well, that is so amazing. It's a low hanging fruit, and it's carbon negative. Like that's such an easy win. I feel like. So kudos to you guys figuring out how to do that, because that's very helpful. Very
important. Look, it wasn't. I didn't figure it out. I met the inventors at McGill, so it was my business partner, Rear Dad, had been working on it since 2012, and then I met him in 2015, and we incorporated in 2016. So he worked a lot on this. In the meantime, he set out with the goal of replacing cement, and then he came upon this, and then realized that you can't hydrate steel slag. So the process of making cement hard is you hydrate it, and when you hydrate it, it gains strength. We cannot hydrate our material. We need CO2. So 20 years ago, people would be like, well, I'm not going to do that. Nobody wants to use CO2 to make concrete. But nowadays, everyone wants to find a home for CO2, right? And we've got this distributable way of storing CO2 all over the world.
Right. Yeah. Now we're trying to use it as much as possible, which is great. Great. You guys have found a use for it in concrete.
Yeah, exactly.
Well, this has been. I've learned a few things, so this is great. I really appreciate you taking time to share what you guys are doing, and it's really exciting. I will be following what you guys do for a while, and hopefully you guys keep licensing more and more, because it seems like such a no-brainer to swap your factory over and have a carbon negative product. And that's
I appreciate your time, Ian, and you following us. Thanks very much.
Yeah, and for anybody that's watching that listens to this podcast and wants to contact you guys, what's the best place for people to find you and make that contact so they can?
You can go to our website, www.CarbiCrete.com. You can also email me at chris.stern@CarbiCrete.com.
Perfect. And we'll make sure those are in the description for anybody who wants to just copy and paste. So perfect. Well, thanks again. Appreciate your time.
Thank you, Ian. Take care and have a great day.